now we want to look at if we have a binomial distribution, when are we allowed to make a normal approximation of it and how to. So let's remind ourselves a binomial distribution is an n number of independent identical trials. R is the number of successes. P is the probability of success on a single trial. And the probability of failure is its complement 1 minus P, we label with Q. So that's a binomial distribution, has these properties regardless. So now, when are we allowed to make a normal approximation of this distribution? We look here. If n times P is bigger than 5 and n times Q is bigger than 5, then we have a binomial distribution that is approximately normal. Our variable is now going to be R. We've seen X as a normal distribution, X bar, the sampling distribution, was approximated by a normal distribution, and now we're looking at the variable R. So what about its mean and its standard deviation? It's approximately normal, and it has a mean of n times P as before. That's our expected value. And our standard deviation, sigma, is the square root of the product NPQ as before. That has not changed. And we have a note here that as the number of trials gets bigger and bigger and bigger, the more close the distribution looks to a normal distribution. So let's look at something where we have a small number of trials, only 3. We're going to look at the same distribution, the same P and Q for different numbers later. N is 10, N is 25, N is 50. We're going to use the same P and Q as from our example with the hot water heaters. P is going to be 0.25 and the probability of individual failure is 0.75. So what we are looking at here is the histogram. Remember, R is discrete. It's a discrete random variable. And so we have nice bars, one for each possible value of R. If n is 3, we could have 0 or 1 or 2 or 3 successes. Those are the only options. And this is binomial distribution is a special kind of probability distribution. So if we add up the heights of these bars, we would get a total of 1. So here, I must say, these look a little bit like minus signs. They're actually all equal signs. Excuse my slides here, and there is a very faintly noticeable square root there that's really hard to see. So let's look at this graph here. These 4 bars do not particularly look like a mound-shaped symmetrical graph that you are used to seeing when you look at a normal distribution. This doesn't look very normal right here. Okay, so let's see what happens if we change n, if we do more trials. The P and Q are not changing, but we're just going to run the experiment now for more times. We're going to look at n is 10. So now n has 0, 1, 2, 3, 4, 5, 6, or 7 showing. There are no bars showing over here for 8, 9, and 10 because it's almost 0. So we're just assuming it's 0. It rounds to 0. The chance of 8 or 9 or 10 successes is so small. Looking a little bit better here. It looks a little bit more mound shaped when we're looking at 10 options, 10 trials. Now let's look at 25 trials. Many, many more. So this looks a lot more like a normal curve. If I just put this curve on top here, it looks a little bit more like a normal curve. It looks much more symmetrical, and it clearly looks mound shaped, whereas we looked at n equals 3, very, very skewed to the right. Ignore this 7.5 for right now. That's just from where I stole the image. And now let's look at n equals 50. Wow, okay. So it's looking more and more like a symmetrical mound-shaped curve, and it looks so more and more like a normal curve. Again, the values that we don't see below 4 and above 22, the probabilities round to 0, so you don't see any bars for those values at all. But it does mean that there's a very, very long tail for these guys out here that we can't draw. So yes, that's also a feature of a normal distribution. So it looks more and more like a normal distribution. So here we are looking at n equals 3 or 10 or 25 or n equals 50 all together, and you can see that as n increases, it looks more and more like a normal curve. Same p, 0.25 for all of them. Let's look at excuse me, over here we have the mu n times p. The expected value is 0.75. Notice 0.75 is too small for us to use a normal approximation. NP must be at least 5 and NQ must be at least 5. Those are our two conditions. Notice here, however, that, or just remember that that is also another way of thinking of mu. Okay, so we can see it looks more and more like a normal curve as n increases, and we have our two conditions that must be met. So if those conditions are met, how do we actually make an adjustment from the variable r to our variable z? So let's look at an example. R is our discrete random variable. We have a bar curve here. We don't have a smooth curve. And let's say we're looking for the probability that r is between 6 and 10, inclusive. That includes 6 and includes 10. So that means we're looking at these darker bars here, 6, 7, 8, 9, 10. So 1, 2, 3, 4, 5. Those are the 5 bars that we are interested in. So what would we need to do? We're looking at these bars and we see that 6 through 10, those 5 bars. We want to actually include those bars. Our z that we're aiming towards eventually is continuous. R is discrete. And this looks like a normal curve. So x is the normal variable we're going to be using, and x is continuous. So that means when I look at the horizontal axis, if I want to include the entire bar of 6 over here, I need to go all the way over to 5.5. Now if I want to make sure that I include the entire bar that's for 10 over here, I need to go all the way to 10.5, between the 10 and the 11. So my r is between 6 and 10. My x variable is going to be between 5.5 and 10.5. I have to increase my range just a little bit so that I include the entire bar for 6, for 7, for 8, for 9, and for 10. So r is discrete. Right now, I've switched from r to x, and I've had to expand my window just a little bit from 6 to 10. I've gone down a half to 5.5, and I've gone up a half to 10.5. This is what we call the continuity correction. The continuity correction is going from our discrete variable r to our continuous variable, our normal variable x. So how do we do it? We convert the discrete random variable r to the continuous normal random variable x. If it's a left point, you subtract. If it's a right point, you add a half. So here's the same example that we just saw from converting here to converting here. So let's look at two examples. The probability that let's assume we can make a normal approximation. Let's say we're going r is bigger than or equal to 3. So are we going to add or subtract here? Let's think about our normal curve. I'll draw it up here. Wherever 3 is, let's say here is your bar that's for 3, and your bar that's for 4, bar that's for 5, etc. If you want to include the entire bar of 3, I have to go down to 2.5. Now let's see what happens if I want to say that, let's say the probability that a variable r is less than or equal to 5. Let me just choose a different color for clarity. So let's say I have a normal curve that's the approximation of a binomial distribution. And it doesn't matter where 5 is. Let's say 5 is here. And I want the values for less than or equal to 5. So that means I do want the bar that is labeled 5, and I want the bar that would be labeled 4, and I'd want everything to the left. If I want to make sure to include the entire bar that is labeled 5, I need to go up to 5.5 between there. So we generally put our variable on the left of any inequality. So let's look at the first example we did for r is greater than or equal to 3. If you're using the greater than or equal to a number, you make it smaller. If you're using the less than or equal to value, you add a half. So this symbol, because we're using r is greater than some value, you subtract a half. Excuse me, let's do this again. And if you're using the less than or equal to symbol, you will add a half, assuming that your r is always on the left. If you have an interval, like we had in the previous slide, then you just make it wider on both sides. So you subtract from the lower and you add to the upper. Okay, so we saw when you can make this binomial distribution approximately normal. That's NP and NQ are greater than 5. And we saw how to do that, which is to change your r to a x. So you're going from a discrete to a continuous. And so you have to change the actual value a little bit by 1/2 up or down. Okay, now continue with a third video, which is the example worked out using this approach.